Hello guys, so in this video we're prompted to find whether the series converges or diverges. And one thing I want you to notice here is that we have a little n right here as an exponent. Every time you see that little n, and I'm gonna leave a note right here. Every time you have an exponent n, it might hint to use the ratio test, to use the root test. We could also apply the ratio test, but the root test is half the work, so that's why it's always good to recognize patterns whenever we're doing series. So just knowing that, and knowing that if I apply the divergence test, notice how these two have the same power. If I apply a divergence test, this is going to diverge to 4/7. So I'm not going to do that step because I already know it's going to diverge. It's going to diverge to 4/7. So in step 1, we're going to go ahead and apply the root test. I don't know why I keep saying ratio, but we're going to apply the root test since we recognize that it's a root test because of the n power. So what do we do for the root test? So basically we have a formula which is right here, which is the limit as n goes to infinity of the nth root of a sub n is equal to L. So the next step, all we're simply going to do in step 2 is identify our variables. And in this case, our variables are a sub n. And a sub n is just simply equal to the function that we have, 4n cubed minus n squared divided by 7n cubed minus 9 raised to the nth power. So what are we going to do now is we're going to plug it into the formula, and we're going to end up taking the limit as n approaches infinity. So that's what we're going to do for the next step. So for step 3, we're going to take the limit of a sub n. So the limit as n approaches infinity of a sub n of a sub n is going to give us a number L. And based on whatever L is, we can apply one of these root test conditions. If L is greater than 1, diverges. Less than 1, converges. If L is equal to 1, it's inconclusive, and we use another series. And notice how those are the same conditions of the ratio test. That is because the ratio test, we can also use the root test. So I'm going to make a note of that. So note, every root test can also be done by a ratio test, but the root test is half the work. So that's why it's always good to recognize what kind of form you have. That's really how series is. It's literally just recognizing what kind of form of series you have and just applying the certain property. So in this case, we have a root test. So I know that a ratio test will also get the same answer, but I want to make life easy for myself and I want to apply the root test. And one thing I did forget to do is the root test is equal to the nth root. So now, without further ado, we're going to take the limit of a sub n. So right here, our a sub n, the limit as n goes to infinity of the nth root of a sub n, of the absolute value of a sub n. And our a sub n is 4n cubed minus n squared divided by 7n cubed minus 1/9. All this is raised to the nth power, and it's all within absolute value. And all this is equal to L. So notice how we have the nth root and the nth power. So I'm going to rewrite this as the limit as n goes to infinity of 4n cubed minus n squared divided by 7n cubed raised to the nth power, and then the nth root, as we know the x root, we can rewrite it as x to the 1/2. We never put 2, but it's always implied whenever we don't put anything. So this is equal to 1 over n, and then n times 1 over n gives us 1. And that's the beauty of the root test, is that the n's will cancel out and you're left with literally just a function. So now we can simplify this even further and rewrite this as the limit as n approaches infinity of 4n cubed minus n squared divided by 7n cubed minus 9. And then to simplify this, we simply just apply L'Hopital's rule. So because they have the same numerator and denominator, L'Hopital rule is going to help us out here. So taking the derivative of the top, we get 12n squared minus 2n divided by the derivative of 9 is 0. The derivative of 7n cubed would be 21n squared. So we rewrite this with our new function. So we have 12n squared minus 2n divided by 21n squared. And notice how we have numerator and denominator, so we're going to go ahead and apply L'Hopital's rule one more time. And the derivative of 12n squared would be 24n. The derivative of 2n would just be 2. The derivative of 21n squared would be 42n. So now, notice how we still have the same exponent, so we apply L'Hopital one more time. So we're going to go ahead and do it again. For this root test, it's exactly very similar to the ratio test, but it's half the work. So 24n minus 2 divided by 42n. And then we're going to go ahead and apply L'Hopital's rule one more time. I'm going to go ahead and clean up all these dots. And basically, whenever we apply this, the derivative of 2 is 0, the derivative of 24n is just 24, the derivative of 42n is 42, and that's our final answer. Not yet though, because we do have to simplify this, noting that these are both even numbers that can be simplified. So in doing so, L came out to be 24 over 42. When we divide both terms by 2, we can simplify this and we get 12 divided by 21, which can further be simplified if we divide both terms by 3 to 4 over 7. And that's our L. So L is equal to 4 over 7. So now that we've computed L, the next step is to, what is it, step 4? Is to apply the root test conditions. So in doing so, when we apply the root test conditions, which I'm going to pull real quick, so we're going to go ahead and put a box around this answer, because this answer is the important answer. And we're going to go ahead and just drag the conditions all the way down here. So right here, our L is equal to 4 divided by 7, which is, and then 4 divided by 7 is less than 1, which means L is less than 1. And since L is less than 1, this series converges. So, and this is our answer. So this series converges by root test conditions. Why? Here, we're going to do this back in retrospect so we can see exactly what we did. So step one was really recognizing it was the root test. And how do we know it was a root test? Because of this n function right here. Because of that n exponent, we knew taking the nth root of it is going to make our lives easier. And so we apply the root test. Recognizing we apply the root test, we identify a sub n, which was just a function. Then from there, we take the limit of a sub n. And in doing so, we will come up with our limit. So notice how the n's canceled right here. They canceled each other out. We did L'Hopital a couple times. And we came out to L being 4/7. Then from there, we just applied the root test conditions. And the root test conditions are right here. And in this case, L is less than 1. So this converges by root test. And if you want to make it more proper, you can put, since L is less than 1, then this converges by the root test. Because on your exam, I'm pretty sure you have to state it like that. So that's the proper way of stating it. But thank you for watching. I hope that was helpful. Hello guys, so in this example, we're going to apply the root test. And we're being prompted to find whether the series converges or diverges. So if you want, you can quickly just test for step 1, and you do it in every step. I'll call it step 0 as a matter of fact, because you do it for every series. So test, apply the divergence test. Which some people can do the divergence test in their head, but if you can't, it's real simple. We just take the limit as n goes to infinity of the function 8n squared over 3n squared plus 7n. And then in doing so, we apply L'Hopital's rule a couple times, but what we're going to end up with as our final answer is basically just this ratio right here of 8/3. And since 8/3 is not equal to 1, or does not equal 0, then therefore it passes the divergence test. So I'll put divergence test is inconclusive. Something like that. Okay, great. So now we know it's not gonna, the divergence test is inconclusive. So what other test is gonna help us? So notice how we have the exponent to the nth power here. Every time you see that, as I put it right here, it's telling us to use the ratio test. Oh, that was bad. It's telling us to use the root test. And we could also use a ratio test, but whenever we have the nth power, we want to take the nth root of it, so the root test will make this a lot easier. So now for step 1, we're going to go ahead and apply the root test. So in doing so, what do we have to do? Well, it turns out that we have to take the limit. So in order to apply the root test, we're essentially just taking the limit as n approaches infinity of the nth root of a sub n, the absolute value of a sub n. So in this case, we're going to just apply this formula, and for the next step, for step 2, we're going to identify all the variables, and in this case our variable is a sub n. So our a sub n is equal to 8n squared divided by 3n squared plus 7n. That's our a sub n. And now that we have it, raised to the nth power. And now that we have it, we're going to go ahead and just simply compute the limit. So that's what we're going to do in step 3. Compute the limit of a sub n, and we're going to call limit L. And based on whatever L turns out to be, we have these root test conditions that are right here. And whatever L turns out to be will determine whether this series converges or diverges. So without further ado, we're going to go ahead and just compute the limit of this. So right here, the limit as n approaches infinity of the nth root of 8n squared divided by 3n squared plus 7n, the absolute value, raised to the nth power divided by the nth root. So in this case, I want you to notice that we're raising something x to the nth power, and we're taking the nth root. So we can actually write this as, I'm going to put a line over here, x to the nth power raised to the 1 over n. And n times 1 over n is equal to just 1. The n's will cancel out. So that's the same logic here. So we can actually just rewrite this simply as, all I'm doing is just cleaning up all these little specks. So we can simply just rewrite this as the limit, and yes, you have to include the limit every single time. It's proper notation. 8n squared divided by 3n squared plus 7n raised to the nth power, absolute value sign, times 1 over n. The n's will cancel out. So the n's should cancel out. And that's the whole purpose of the nth root. So I'm going to make note of that. So note x with the n power n root should always cancel out. If they don't cancel out, that means there's something wrong with what you did. So they should always cancel out. So in this case, what are we left with? We're left with this limit. So the limit as n approaches infinity of the absolute value of 8n squared divided by 3n squared plus 7n. You can do this in your head, but I'm going to do this the correct long way. So notice how we have the same powers. So we have 2 as the highest power for both functions. So in this case, whenever you have it, or always, you apply L'Hopital's rule. So that's what I'm going to go ahead and do right here. So in doing so, when we apply L'Hopital's rule, we get the derivative of 8n squared would be 16n. And the derivative of 3n squared plus 7n, the derivative of 3n squared is 6n, the derivative of 7n is just plus 7. And that's our derivative. But we have n in both terms, so we're going to go ahead and do this a second time. So the limit as n approaches infinity of 16n divided by 6n plus 7. So when we plug in infinity both times, we get infinity over infinity, which means we apply L'Hopital's rule again. And in doing so, 16n, the derivative of 16n is just 16. The derivative of 6n plus 7, the derivative of 7n is just 0. The derivative of 6n is just 6. And this is equal to L. So right here we've identified L is equal to 16 over 6, and we can reduce this by dividing both terms by 2, and we get L is equal to 8 over 3. And that's our L value. So I'm going to go ahead and put the yellow rectangle around it so that way we know that it's our L. So now that we have that, the next step for step 4, now that we have our L in step 4, we're going to go ahead and apply the root test conditions. So what are the root test conditions? Well, you don't have to memorize them. You just have to get used to them. As I always say, in math, there's no memorizing. It's just a lot of getting used to. So I'm just going to copy and paste them down here. So now we have our conditions. So in this case, what was our L equal to? Our L was equal to 8 over 3. And 8 over 3 is well greater than 1. So since L is greater than 1, according to the root test conditions, this series will diverge. Diverges by the root test. And that's how you would write it on an exam. You put diverges by root test. And that's the final answer. So that's how you apply the root test. So in quick retrospect, I'm quickly going to go over everything I did for this problem in like a nutshell. So right here, the first thing we did in step 0 was we do it for every series, we applied the divergence test. And divergence test proved to be inconclusive. And once it proved to be inconclusive, then we move on to step 1. We apply the root test. Why? Because we have an a sub n raised to the nth power. So in doing so, we were able to identify a sub n in step 2. And in step 3, we applied the root test. And then we did L'Hopital's rule a couple times. We made a note right here stating that the nth power and nth root should always cancel out, which is what we did right here. And then we got our L, and our L was computed to be 8 over 3. And whenever we did that, the next step and the final step was just simply to apply the root test conditions. And since L is greater than 1, we're simply just applying the root test conditions. This specific series diverges by root test. Note, the ratio test can do the exact same thing, but the root test is half the work. Thank you for watching. I hope that was helpful.